So let's get going. This is a cool concert that I found. It's like in some cave in like Norway or something. Wardrun is like kind of a folk Viking music kind of band. And Aurora, of course, pretty famous. All right, let's look at your quiz results. The De Morgan assignment was pretty cool. It was interesting seeing how many different solutions you guys came up with for that. I'll just go over a couple important things. First of all, if you ever have code that looks like this, you can simplify that. Likewise, you don't ever really need to have like an if something return true, else return false. First of all, you can always just do 1 and 0, right? That'll cut down on some characters. And then second, just return whatever is within that. And then you can save all those characters. Okay. So if you want to return X or with Y, two vertical slashes is OR. However, the bitwise OR operator will pretty much do the same thing as a logical OR in this case. So yeah, you can use 1 vertical slash instead of 2, and then like you can see on the solutions over here, if you use the hashtag define thing, there's all sorts of horrible broken things you can do to your code to compress it down further. That's why I had 2 different functions, by the way, so the use of hashtag define would be worth it to kind of shrink it down. Okay, so any questions about the De Morgan assignment? Feel like you're writing Python. It's funny. Yeah, code golf is a fun thing. It's you know, I don't think that the actual assignment was very hard for De Morgan. It did look like a few students didn't do it, which is kind of disappointing because it's like just doing it. It's not hard. Like I give you the answer, right? Like here's the if statement. You just gotta simplify it a little bit. So incredible to see all the ways you can shorten the character count. Yeah, it's fun. Yeah, and a number of students beat me too, and I thought my solution was pretty good, you know. But there was a couple students that did better than my 65. Yeah. So let's see how y'all did on the quiz, because I said this is going to determine whether or not we talk more about logic or move on to graph theory. All right, not bad. Not bad. Okay. There is actually one more thing that I didn't mention, which was the difference between validity and soundness. Let me talk about that. Then we'll move on to graph theory, which is my favorite topic in this class. So, okay, so when you evaluate an argument, there's actually 2 things you need to evaluate. And these are sort of orthogonal to each other. And the fact that they're orthogonal, they're not really the same question at all, gets a lot of students. And so there's 2 things when you're evaluating an argument. First, does the logic work? You know, all pirates can swim. Alapizco can swim. Therefore, Alapizco is a pirate, right? The logic on that does not work, right? And if you draw it out, you know, set theory-wise, you have the set of all people that can swim, and you've got pirates who can swim, or actually, what I say, all pirates can swim, Yeah, so pirates would actually be here. And then I say Alpisco is somewhere within can swim. So he could be either a pirate or not a pirate, right? So the best you could say is Alpisco might be a pirate. You can't say he is one because he could be something else that swims that isn't a pirate. Yeah, so that would be an invalid argument. The other question is, are all the premises correct? So if the logic's correct, we say the argument is valid. If the argument is correct and all the premises are true, then we say it's valid and sound. And if the logic doesn't work, it's invalid. So there's three options. There's invalid, there's valid, and there's sound. Sound and valid. Well, sound for short. So let's go through some examples of this and let's see what y'all think. Okay. Premise 1, Socrates is a man. Premise 2, all men are mortal. Conclusion, Socrates is mortal. What do you think? And I'm not one of those people interested in splitting hairs. Well, it hasn't been proven that all men are mortal because, I haven't died yet, So Aaron's going with valid but not sound. Which one of these premises do you disagree with, Aaron? You don't think that Socrates was a man? Said is a man. Again, I'm not super splitting hairs here. Connor, Harry, valid and sound. What premise do you disagree with, Aaron? Premise 1, premise 2, both. Premise 2, all men are mortal. Okay. Why do you disagree that all men are mortal? We'll do the Socratic method here. Maybe we can upload our brains into computers someday or something. Premise 1, Socrates is a man. You disagree with premise 1? Not all men are immortal. Not all men are mortal. Immortal? It doesn't say immortal. It says mortal. Socrates is a man. All men are mortal. Socrates is immortal. Okay. Yeah, I would go with sound for this one. All right. Next, all birds can fly. Bats are birds. Therefore, bats can fly. Is this valid, invalid, or sound? Remember the two questions. Two questions. No. Invalid. Yes. So here's how you approach it. Does the logic work? Yes or no? If it does, are the premises true? This is the flow chart for evaluating an argument. Okay. Invalid because bats are mammals. Invalid because bats are not birds. That's a very common mistake that people make, which is that they just look at the conclusion and they're like, or they look at a premise and then they say it's invalid. All birds can fly. Bats are birds. Therefore, bats can fly. It's the exact same argument, actually, as this one. Socrates is a man. All men are mortal. Socrates is immortal. Socrates is a bird. All birds can fly. Therefore, Socrates can fly. It's the same form of argument. So it's a valid argument. It is not sound, however, because bats are not birds, and also birds cannot. Not all birds can fly. There's the kiwi bird that can't fly, the ostrich, the emu, things like that. So actually, both of these premises are wrong. However, the logic is correct. The logic is exactly the same as for the Socrates argument. Socrates is a man, all men are mortal, Socrates is immortal. Socrates is a bird, all birds can fly, therefore Socrates can fly. Same argument, just the premises are wrong. Right. So this one is valid but not sound. All cats are mammals, all dogs are mammals, therefore all cats are dogs. What do you think? Valid, invalid, or sound? Premises are true, right? All cats are mammals, all dogs are mammals. Does the logic work? Not necessarily. There could be some overlap. We don't know if there's any overlap between cats and dogs using this form of the argument. However, we cannot conclude that all cats are dogs because they're both subsets of mammals. We don't know if they overlap within the set of mammals. They might be, but we don't know that. What is the difference between not sound and not valid? So here's the flowchart again. So if the logic does not work, it's invalid. End of story. If the logic does work, which it does, the form of this argument is valid. All birds can fly. Here's a set of all people that can fly. Birds are inside of it. Bats are birds, so bats are inside of the set of all birds. Birds are inside of the set that fly. The logic works. So then you have to then examine the premises. Are the premises true? Is it true that all birds can fly? No. Is it true that bats are birds? No. So this is valid but not sound. If the premises were true, like with the Socrates thing, then the logic works, the logic is valid, and the premises are true, therefore it is valid and sound. So for this one, the logic does not work, so it's invalid. And you can stop there. You don't need to worry about the truth of the premises, because if the logic doesn't work, it's a worthless argument. Okay. If Socrates was a philosopher, then he wasn't a historian. Socrates wasn't a historian, therefore Socrates was a philosopher. What do you think? X implies Y. Y. Therefore X. This is invalid. This is called an affirming the consequent. Even if we accept the first premise, which I don't think is true, I think he can both be a historian and a philosopher at the same time. He could have, if he wasn't a historian, he could have been like a stonecutter, which I think he was, or he could have been a musician, right? Even if we hold your career to be mutually exclusive, then just because all we know is that he wasn't a historian doesn't allow us to conclude that he was a philosopher. The implication is this way, left to right, not right to left. It's not a biconditional. Okay, so that's invalid logic. All engineers enjoy ballet. I'll just give you that one. That's a false premise. So it's either going to be valid or invalid, but not sound. All engineers enjoy ballet. Some males are engineers. Therefore, some males enjoy ballet. It is valid but not sound. Very good. Okay. All right. So I'll probably do something on that. Okay. So let's talk about graph theory. Okay, so graph theory, like I said, is my favorite topic this semester. So we'll be spending a fair chunk of time on it. And if you need to spend more time on logic, let me know. But this is what is Math 11? What is Math 11? I don't know. Stats, I guess. I don't. Yeah, it's funny. I've been teaching here for like, I don't know, 7 years or something, and I actually don't know what the different numbered math courses mean. Math 5, 4A, I don't know. I just let people say the numbers, and then I try to infer what they mean from context. Okay. No, I don't teach any math classes. They actually hired me originally at Fresno City College because they were hoping that I could teach algebra. You know, like algebra. 7th grade, 8th grade math, you know. And they didn't let me. The math department said I was not qualified to teach algebra. So, because I do not have a master's degree in math. You have to have a master's degree in math to teach algebra. So, I'm like, you know, I actually didn't mind because I actually didn't want to teach algebra. But it's like I'm submitting all these graduate math classes I've taken. You know, nope, you don't have a master's degree specifically in the subject. You do not have the ability to teach algebra. So I was like, all right, cool. Imagine showing up for algebra and I start doing modular division. Just explode their brains. 4A is geometry, 4B is pre-calc, 5A is calc, 5B is more calc. Okay, cool, good to know. Thanks for explaining it to me. 4A is trig. Okay, so yeah, today we're going to be going over graph theory, which is fun. There's no midterms anymore, so yay. I did get up another competency exam, I think, but I need to do more of those. All right, so let's talk about graph theory. What is a graph? I'm sure you guys have seen these before, right? Like a graph, you know, like graph it out, you know. No, that's not what we're talking about. When we talk about a graph in graph theory, it has nothing to do with like bar charts and line charts and stuff like that, you know what I mean? Look at this graph. That's funny. I have a picture. What is it? What was that, Nickelback? Yeah, okay. So this is a graph. In graph theory, a graph is a bunch of vertices connected by edges. So points and lines. And that's it. That's all a graph is. And look at this photograph. Yeah, perfect. Yeah, good use of the meme. Except it's the wrong kind of graph. It needs to be a graph theory graph. So somebody needs to Photoshop that on. All that matters on a graph is which points, which vertices are connected to which other vertices. You could actually draw this graph however you wanted, and it would not change the meaning of the graph whatsoever. So if I were to label this graph, this is A, B, C, D, E, F, G. I could redraw this graph if I wanted to without changing the meaning at all, like this. Here's A, Here's B. Here's C. Here's D. And C is connected to D. Okay. Then E. E is connected to C and D both. We'll put F down here, because why not? F is connected to E and C. And then G is connected to F and E. Okay. So this graph here on the right is the same as the graph on the left. I've changed how it's drawn, but it's the same graph. Does that make sense to y'all? All that matters is the vertices and their connections. Or when you can pull them around and move them around however you want. Okay. So, for example, what does it mean? You know, for example, have you guys ever heard of the was it 6 Degrees of Kevin Bacon? Have you heard of that kind of meme thing, where like everybody in Hollywood is within 6 connections of Kevin Bacon? So the notion is everybody in Earth has like 6 degrees of separation from each other. So like you might not be aware of it, but like if you like think about the people you know, and then like the people that they know, and the people they know. There's at most 6 hops between you and some remote villager somewhere in the world, right? So, for example, you know me. My dad knows David Kendall. David Kendall is Bill Clinton's lawyer. So that's 1, 2, 3, 4 hops from you to Bill Clinton, or Hillary, for that matter, who's Hillary's lawyer as well. So, and then from there, you know, you probably get anywhere in the world, you know. And who knows, there might even be a faster path than that, right? So, let's see, from you to Arnold Schwarzenegger, let's see, you to me to former pastor at my church in high school. Her daughter met Arnold Schwarzenegger. That's 1, 2, 3, 4. So you're 4 hops away from Arnold Schwarzenegger. And then degrees of Kevin Bacon. Arnold. So yeah, all of you guys in this class are 6 degrees away from Kevin Bacon. So there you go. So Arnold Schwarzenegger was in the movie Dave with Stephen Garash, who was then Murder in the First with Kevin Bacon. So, because you're 4 hops from you to Arnold Schwarzenegger, maybe there's a faster route. He was governor of California, so there's probably a lot of different ways you could be connected to Arnold. But when he was thinking about running for governor, the daughter of the pastor at my church at the time said something like, "Well, I'll vote for Arnold if he shows up at my house." And he heard about this, so he showed up at her house with the film crew and all this stuff. And she's like, "All right, I'll vote for you." So you to me to pastor. Yeah, four from you to Arnold, and then 2 more to go to Kevin Bacon. You're confused why this is a thing? Yeah, well, there's like I said, there's a philosophical concept that that you're no more than 6 hops from any person on Earth. Like, we're all connected, right? And then it became a meme to do like, how far away are you from Kevin Bacon? And so has to be in a movie, not just TV shows too. Okay, and so your Bacon number is how many hops you are away from Kevin Bacon. And so all of you have a Bacon number right now of 6, unless you can find a bigger one. every couple of weeks, the Oracle downloads every English language article from Wikipedia. We then parse it, and it does a BFS to find shortest paths, which we'll talk about today. And so, yeah. So it runs on an Amazon EC2 node. It consumes 500 megs of RAM. Okay, so there you go. This is actually a graph theory algorithm to do that. Okay. So, if Kevin Bacon was here, if Kevin Bacon was A, then B and C would have a Bacon number of 1. D would have a Bacon number of 2. E and F would also have a Bacon number of 2. Because you can go A to C to E, A to C to F. And then G would have a Bacon number of 3. Do you guys see that? Because the shortest path between A and G, C to E to G, or... yeah, I think that's the fastest one. Does that make sense? Like, conceptually, does that make sense to you? So, the people in Hollywood would be the dots, and then the movies they're in, like Dave or whatever it was for Arnold, are the lines. So the relationships are the lines, and the dots are the people, the actors and actresses in that one. Okay, but they can represent kind of like anything. If you're doing, I don't know, like navigation, like Google Maps uses graph theory to find the shortest route between two different points, then the dots would be like cities, and the lines represent how far away the cities are from each other. Facebook has what's called a social graph, and each vertex represents a person on Facebook, and the lines represent friends, right? And so you can traverse the social graph to find interesting things out. And that's a big part of like what Facebook does, right? Like if person D is suddenly getting into like health food, things like obesity and exercise actually spread virally. I don't know if you guys knew that. But if your friends start exercising and losing weight, then the studies show that you're more likely, not necessarily, but more likely to start eating healthy and exercising as well. And there's probably a direct effect, like your friends are like, no, let's not go to this horrible, unhealthy restaurant. Let's go to a healthier restaurant. So there's probably some direct effect, but a lot of it is just, it's viral, right? So you see your friends posting on Facebook, they'd put on the COVID-19, you know what I'm saying? And like they're losing it. You're like, oh, damn, that's cool, and they're 5 a.m., time to hit the grind, trends, yeah, but all these things like spread virally. And so if you're Facebook, you could be like, okay, well, Chuck Grassley, the 80-something-year-old senator from Iowa, just posted, it's 5 a.m., time to go for my run. And then these people are friends with Chuck Grassley. So it would be like, all right, let's sell health food to these people. That makes sense? So if your friends are suddenly interested in something, they're posting health food, videos and things like that, then you can traverse the social graph and better serve ads, right? Which is the point of Facebook, right? The point of Facebook is to give targeted ads at people that will get clicked on. Facebook makes more ad money than a lot of countries in the world, right? So we should not have 80-year-old representatives. He's a senator, not a representative. And if he's running for re-election again, and he'll be in his 90s by the time the term is over, should he survive. So, are we going to talk about the tricks they use for traversing these things? Yeah, we're going to talk about the algorithms because they're pretty cool. So the hardest thing actually in engineering Facebook, according to Mark Zuckerberg's talk, Harvard talk. He was a student at Harvard, and I think he dropped out to do Facebook. He went back and gave a talk, just like one of the computer science classes, like a few years after he made it big, not like when he was like, having more money than you know, most countries. It's actually a really amusing talk, just because this one, yeah. So it's 2005. So this was not when he was like, he was a successful, but he wasn't like mega successful. And he's just look at how packed that audience is. If it was today, you know, the whole thing would be like wall-to-wall students. But this is, you know, the professor's probably just like, oh yeah, this guy named Mark Zuckerberg's coming in. You can ask him questions about like how, you know, what kind of, you know, database he uses or something. It's a computer science class, right? Which I think is like, at Harvard, I think CS50 is like topics in computer science or something. And like nobody shows up. Is this going to be on the final? Nah, just come if you want to. Yeah. I watched that whole talk. Like, it's actually pretty good, because they're asking him like technical questions, like, you know, do you do this and this, and he's like, oh yeah, and he's, you know, he's answering the questions. This is CS50. Let's see here. What is CS50? Can I audit it? Oh, they're teaching Scratch. So this is like a super basic. Raise, yeah. So this is like their really basic like intro to programming class at Harvard, and just like nobody showed up for the Mark Zuckerberg lecture. And like as he's talking, like people are just like tapping away on their laptops and stuff like that. Like it's just, you know, there's like 15 people there or something. It's too funny. Hardest thing was fighting the lawsuits. Yeah. So. Such an awkward talk. Yeah, I don't know. Like, I actually found it interesting because, you know, you can tell, like, he actually was, like, technologically involved with, like, every aspect of the company. And then one of the points that he made was actually, like, you have to hire good people, right? Because, like, the trouble with this is, like, you can have a graph that works for, like, Harvard. You know, you could probably hold all of that in one computer. But now, like, you expand to Yale and you expand to the other. Because Facebook was originally just for colleges, right? And what he found was that like the size of this thing can kind of grow exponentially, you know. And so what they did was they just kept Harvard and Yale on different servers, you know, to manage the growth of the graph. But then if you're going to start allowing everybody in the world to be on this one graph together, like how do you manage that? Like there's like 2 billion users of Facebook a month, right? Like, how do you put that onto a computer? You know, how do you traverse it? How do you, like, that's actually a really hard problem. You know, it's really easy to create little toy problems or toy, you know, things that'll work on, like, you know, 1,000 people or whatever. But when you have 2.1 billion people a month using your website connected to each other, somebody uploads a photograph and that appears on the feed of, you know, all of their friends. Like, that's a heck of a scaling issue. And he said one of the important things is just to hire people that really know their stuff, you know. And that's what Facebook did, and they were successful, obviously. Other social media companies like MySpace and Friendster folded. Friendster folded in part because they couldn't scale very well, from what I understand. I never used it. Time to make that your next homework assignment. Facebook? You want to do Facebook or Twitter? Which one? Because they're different, right? So we'll talk about that in a second. But in Facebook, if you're friends with somebody, the friendship is bidirectional, right? So do you understand? Like, if I'm friends with Arius, then Arius is friends with me, right? But on Twitter, you follow someone, right? And so with Twitter, you put little arrows on the graph like this. So person C is following person E, and person E is following person F, and person F is following person C, and maybe person E follows person C back, and things like that, and you have what's called a unidirectional graph. So Facebook and Twitter are a little bit different, right? And then on Facebook, they added following also, because you would run out of friends, because Facebook has a limit of like 5,000 friends, or they used to, I don't know if they upped it. So like I'm friends with Brandon Sanderson, who is one of my favorite authors. I helped him out on his book tour for the first Wheel of Time book back in 2008 or something like that. And so we've been Facebook friends, but he ran out, like, because when he was a new author, like if somebody added him, you just add them, as a friend, sure. And then he very quickly hit his 5,000 person limit after he started working on the Wheel of Time series, by the way, which is coming out on Amazon Prime, I think, relatively soon. And so he couldn't add. He's like, I'm sorry. And then whenever he needed to add somebody he knew in real life, he would drop a random fan. He's like, I'm sorry. Like I need to add my personal trainer on here, whatever. So he would apologize. He was a very nice guy. Like Brandon Sanderson is probably the most nice, humble, polite individuals I've ever met in my life. And I've encountered him a few times and talked to him. Like I ran into him at the airport this one time, and I'm like, hey, and he's like, do I know you? I'm like, yeah, I was on your book tour. He's like, oh yeah, that's right. You want to play Magic the Gathering? I'm like, I'd love to. So he's just a super awesome dude. And so like if he has to drop people, he's just like, I'm so sorry. I need to add these people. And so when Facebook added in following rather than just friends, then it allowed a lot more people to follow Brandon Sanderson because that's a different relationship. It's probably easier on their servers too, is my guess. So that change, it's probably a scalability thing. Like they limited the degree of these nodes to 5,000, so you can't have more than 5,000 connections coming out. Or that was the limit back then. I don't know now. Big name drop. I guess it's not like we hang out, but he is a really, really cool dude. Like on the book tour, like we were standing there outside the bookstore, and he just stood there till midnight answering questions. Like people just kept peppering him with questions, and he just sat there. He's like, I will stay here until there are no questions left. And it was literally midnight in Half Moon Bay. And he's like, sure, no more questions? And I'm like, oh, I've got one. He's like, sure. And yeah, super fantastic dude. If you guys like reading fantasy, I can highly recommend Brandon Sanderson's work. They're very cheerful and upbeat, kind of the opposite of George R. R. Martin in that sense. Okay, so graph theory is very popular in movies. These things look like alien sigils and things like that. So if you look at like what was it, the Marvel Agents of Shield, Agent Coulson is like possessed by like some alien. He starts writing graph theory on the walls and things like that. Mistborn's a good jump off book, yeah, for sure. Yeah, it's a good intro. Elantris is good also. The Stormlight Archives are a little bit meaty. Each of the books is like that big. Like he has to find out from the publishers the maximum size of a spine of a book. Yeah. Okay. So, all right. So what do the vertices and edges represent? They represent something. The vertices represent something, and the edges represent a connection to something else. It could be a Facebook friend. It could be two cities connected by roads. Is it pretty broad? Yeah, that's pretty broad. Graphs are used everywhere in programming and mathematics. This is, like I said, this is my favorite topic. And it's my favorite topic because it just comes up in so many different areas and applications and things like that. So you can use graphs to represent what states connect to other states, right? So if you have one node representing California, then it could be connected to Oregon and Nevada and Arizona, and Oregon could be connected to Washington and Idaho, and Washington's connected to Idaho also, and then it blocks Montana, I think. Yeah, Oregon to Idaho, Washington. Yeah, it blocks Montana up there. Yeah. And Oregon to Nevada, Nevada to Idaho. Yeah. So you can make a graph having all of the states in the continental United States. And does this make sense to you? So like the edge represents they're bordering each other. The vertex represents the state. The edge represents that they are touching on the map. Does this make sense? Okay. Good, because a friend of mine who used to work at Microsoft, this was his job interview question. So a lot of companies love using graph theory to hire you. So he's not working there anymore, so I'll give away his job interview question. And so his job interview question was, he would hand you this graph, of all the continental United States. And he would say, what is the biggest word you could spell if you were able to start anywhere on the continental United States and you could pick out one letter from the state, like let's say A from California, and then you have to go to the next neighboring state and pick out a letter there. Like from Arizona, we could pick out the R, and then maybe we'll go up to Nevada and pick up the E, and I don't know where I'm going with this. R, that's a word. There we go. So it's a three-letter word. A three-letter word in the English language. What is the longest such word you can spell? You have 15 minutes, begin. Yeah. So that bugged me for years too, because I was sitting there thinking about it. Like, man, how do you do that? Do you start with the alphabet? Or, do you start with the dictionary? On Unix, there is a dictionary that holds all the words. Like, would you run through all of those, or would you go here and I don't know, it was something that I chewed over in my brain for a long time, And I don't expect you guys to know how to solve this yet because you haven't learned graph theory yet. But that'll give you the idea of what kind of job interview questions you get. And that's a hard one. And partly he doesn't expect you to solve it. Right? And that's something all of you need to keep in mind. My brother-in-law, his job interview question was he hands you a file holding 100,000 phone numbers in it, formatted all differently, some with hyphens, some with parentheses, some with spaces, some with not spaces. And you have 15 minutes, identify which ones are phone numbers, which ones are not phone numbers. Go. And you're not expected to solve it necessarily. I'm like, did anybody ever solve it? He's like, yeah. A couple people. I'm like, did you hire him? He's like, yeah. Definitely. This guy just went and wrote an entire program up on the whiteboard in 15 minutes. And my recommendation was, must definitely hire this person. And the person apparently went on to do great things at Microsoft. So, but it's like those questions where they try to get an idea of how your logic works. They want to, not logic exactly, they want to see how you go about trying to solve the problem. And so whenever you do one of those things, it's good to think out loud. Take a moment to think silently, so you don't say something completely dumb up front. But ask questions, and while you're asking questions, your brain's kind of chewing on it also. Okay, can we take multiple letters from the same state, or does it have to be one from one state and one from the next? Can we start at any state? Does it have to be the first letter in the state or any letter in the state? You can ask questions, and that's part of it actually. They want you to ask questions. They want to see how your brain works. Can you specify the problem nicely? Can you because if you just all right, I'm just gonna go, and you do something and it's the wrong answer, that just looks really bad. Because that means you're gonna be wasting their money, right? Oh, sure, I can solve that, and you solve some other problem. Asking questions is really good. And then when you start solving it, you're like, yeah, this is a tough one. Let's see. This kind of looks like a graph theory problem. What algorithm would be good for solving this? Do you have a dictionary for me? Or do I have to figure out the English language? Or is there a file that has a dictionary? And they'll be like, assume you have a file that has all the text, of all the English words. Okay, thank you. All right. Yeah, maybe I can turn this into a regular expression. If I turn it into a regular expression, but how would I do that? You know, and they want to see how the thoughts are turning in your head, right? That's what they're interested in. They're not expecting you to solve it. They want to see how you think, and if given reasonable amounts of time, you would be able to solve it, right? And if you have just no clue because you've never taken CSI 26, sucks to be you. A lot of job interview questions are from 41 and 26. Okay. There's a lot of data structure questions, and there's a lot of graph theory questions. Okay. Run all the states from the first state to see the potential words. Yeah, you could brute force it. You know, I'd say I might even start with that. I'm like, okay, let's see, brute forcing it would probably be impractical, you know, but how would we do that? Start in Washington, do a traversal through the graph, trying every possible letter. Seems implausible. You know, like, but that's what they want to hear. They want to hear you speaking out loud. If you just sit there and stare at it like this, like, that's not helpful, right? Maybe you're solving it in your head, you know, but to them, you're just like staring at it like this. And they think you have no clue, right? So, yeah, job interviews are one of those things. Talking out the problem you're solving, yeah, they're curious how your brain works, because computer science is about your brain, right? It's a, you know, it doesn't matter how tall or short or thin or fat you are. Like, it doesn't matter. Computer science is very much a discipline of the mind, and they're hiring people that are smart. And that's one of those things Mark Zuckerberg said in his sparsely attended talk at Harvard, was that you have to hire people that are smart. You know, find people that are good at solving problems, and then trust them that they can solve it. You know, always keep an eye on them, but, you know, let them do their thing. You know, so make an AI. Yeah. Okay. So these things could be roadmaps. They could be logic blocks and circuits. What? Yeah. Everything ties together. So, like, yeah, you have an and an or and a XOR or something. Yeah, this is a graph, right? Like circuit diagrams are graphs, and traversing a circuit is a graph theory application. Okay, pathfinding for sure is graph theory. Okay, so another famous problem is the four-coloring. Can you color a regular map? A regular map means you don't have, like, Michigan, right? Do you know what the problem is with Michigan on a map? Or maybe Hawaii if it was within some other state. What's the problem with Michigan? A lot of problems. Well, it's split up, right? Like, there's two different geographical segments to it. So the graph coloring, which was by this guy named De Morgan, I don't know if the name sounds familiar to you or not. No, you can have multiple connections, but the question is, can you color a map such that no two states touching each other have the same color? Right? So blue, red, right? You can have two different blues, they just can't be touching each other. You can have two different yellows, can't be touching each other. Two different greens, can't be touching each other, right? Like, you can have multiple reds. We have 3 reds actually, but they just can't be bordering each other. So is it possible to color a graph such that, for a regular map, right? That means no Hawaii, which exists within other states, and no Michigan, and it's split up into multiple parts, things like that. Just a regular, you just have regions like this, right? If you have a regular map, can you four-color it? And I think the answer is yes, actually. So, applying the Voronoi algorithm, Voronoi wouldn't work. The actual, because here's the thing, the regions actually don't matter. The the actual physical representation doesn't matter beyond just using that to get a... this actually could be a Verona. No, it's not. But all that matters is the graph, right? Which states border which states. And then you go through and you just color the graph. And color it in such a way that no two nodes share the same color on the same edge. Shortest paths is what Aaron was talking about. Are we looking at the graph? Yeah, so yeah, the actual regions don't matter. And this thing, I can see why you think it looks like the Voronoi thing, because it's pretty close to one, except there's a couple convex or concave regions, whatever, here and here. Like those can't exist. But the rest of it could be a Voronoi diagram. But when you're given a map to color, and that might be a fun assignment. I actually give that to my CSI 1 students. Here's a map, do it for coloring of it. The actual map doesn't matter. What matters is this. So you transform it from a map into a graph, and then you use a graph coloring algorithm to color it in such a way that no two vertices that are connected to each other have the same color. Kearney, where you would be working if you weren't teaching? Yeah, I mean, I still have my own business and stuff. So I'd be doing more of that, probably making more money, but it's fun. It's fun teaching. Where would I be? Where would I be if I wasn't teaching? Yeah, probably running my own business again. I mean, I still am, technically. It's really nice working for yourself. I mean, I don't mind working for the college that I work for right now. They're really good to work for. They treat me well. I work hard for them. We get along great. But working for yourself is really nice too. Consulting. Yeah, basically, I do work. I do a little bit of this, a little bit of that, and pays pretty well. So it's nice when you're the boss. You don't get paid hourly. You just, if there's a task and they're going to offer you $5,000 to do it, if it takes you an hour to do it, you just made $5,000 an hour. If it takes you a week, your hourly goes down proportionally. So it's. I actually think that task-based payments in computer science make a lot more sense than hourly. Because if you're paying somebody hourly, you're incentivizing them to take longer, right? So, a video game company, maybe. Video game companies don't actually pay that much comparatively. People want to work in the video game industry because they can make video games, but video game companies, on average, pay less than the computer science industry. Not for like a big tech company. I mean, if they offered me enough money, probably. But I've never had a desire to work for Google or Microsoft or Facebook or Apple or Amazon. I talk to, I have friends at like most of these companies, and it's not like they're bad companies to work for. It holds like no appeal for me. So, don't let me stop you. Like, they pay pretty well. Like you make pretty good money, especially now that everything's online. You don't even have to leave Fresno if you don't want to. You can work remotely for most of these companies now, which is nice because the Bay Area kind of. I don't want to say the Bay Area kind of sucks because it's not exactly true, but it's expensive as all hell. We're gonna have to take a break anyway. So let's just pull up Zillow for San Ho. All right. Let's see how much houses are in San Ho right now. The housing prices are actually not as bad because of the pandemic, because people have been leaving the Bay Area, right? If you look at housing prices all throughout California, they're shooting up. In the Bay Area, they're kind of flat because of the remote work thing. So I worked with San Jose also. I've worked with a lot of places around the country. Yeah, so 5 beds, 1.8 mil. 4 beds, 1.5 mil. 3 beds, 2 beds from 1 mil. 2 beds, 1 mil. 2 beds, 800K. Yeah, not cheap. Not cheap. And then if you come up into Palo Alto, then 4 beds for 3.5 mil. Yeah. It's an okay looking house, I guess. It's like nothing to write home about. You know, like in Fresno, this is just like your average house in Fresno. You know, you're driving down a road and like you're not going to be like, oh wow, look at that $3.5 million house. You know, it's just a house. You know, pleasant. Yeah, so the Bay Area is ridiculous. Here's a $5 million house, and that it just looks like any other, like, you know, Spanish style. Nice backyard in Palo Alto. Yeah, you probably pull that out and put an apartment complex and make your money back. It's a cool little fireplace. I like it. Yeah. That's easily 5.3 million, right? It's worth it. And 18 million. Jeez. Yeah. So working at FANG companies, we're talking a lot about, yeah, but I mean that's my point, and then we'll take a break. Is that like, yeah, my friend that worked at Microsoft, his wife worked at HP, and they were living in like a, I don't want to say run down, but they were in like, you know, a 1 or 2 bedroom apartment, you know, like for years, because you can't afford a house, you know, and so, you know, like you're making good money, like they make good money. Both of them were making good money, and they worked and they lived like college students for like 10 years, you know, saving up money. So it's like, there's that, you know. Were they in Bellevue? They're in Mountain View. Bellevue's up in the Seattle area, which is nice too. Bellevue is it's nice. I used to go up there every year for CPP Con, or for 2 years, I guess, not every year, but for 2 years. And yeah, Bellevue's nice. No, they're in Mountain View in the Bay Area, and just like in an apartment complex. Like I was staying in an apartment complex in Fresno at the time. Like it's not like our digs were any different, you know. We're basically staying in equivalent housing. You know, one was in Mountain View and one was in Fresno. You know, so mine was cheaper, and they were making more money working for, you know, HP and Microsoft. So I don't know. I mean, it's all worked out pretty well, I think. But yeah, with the remote work now being a thing, you could live in like Nebraska if you wanted to, you know. So it's actually opened up, I think, a lot of living arrangements that were impossible before. So it's one of the benefits of the pandemic, I guess. A lot of my students, when I started teaching, have been graduating, and a couple of them I saw over winter break last December, and then I met with some more over summer break. And yeah, they got hired to be computer science people, and they've been into the office like once. Yeah, like they got hired, they walked around like, oh, look at this company, this is so nice, and then they moved to Colorado. Yeah, and so the 4 of them are working for like different. They're working for like different companies, and they're just living in a house in Colorado together. And it's like, okay, it's cool, you know. Way cheaper than San Diego, you know what I mean? So, yeah, the pandemic has definitely had some benefits, because housing is stupid. Housing in the Bay Area is some of the dumbest housing prices in the world. And so, if you got family out in Michigan or something, you know, I don't know. There's lots of opportunities now. Okay, so we will pick this up in 11:20. Okay, let's go ahead and take a break. And if you have any other questions about hiring and, you know, working and stuff like that, just post them. We got a long class today, so we can always go off on a tangent. It's fine. See you in a bit. All right, welcome back, everyone. So some questions asked during break were sites to prepare for it. So there's a couple ways to prepare for coding interviews. First of all, watch these lectures, because especially the next couple ones, which are going to be on graph theory. But there's websites like HackerRank, LeetCode, Code Wars, things like that, and that's good preparation for programming questions as well. There's also cracking the interview code, which you can find on Amazon, that'll help you prepare for job interviews and things like that. In general, though, my advice is to make sure you really understand the stuff from 41 and 26. And just think out loud. Like when you're solving these things, just work them through how you're thinking about it and how you're solving it. That's kind of the main thing. Okay. So let's see. How close are Code Wars to being actual interview questions? I wouldn't be surprised if they're pretty close. It depends how hard they are and stuff. No more Grente gaming. Okay, so C#. Most game engines or video game stuff uses C#. I don't know if I'd go that far. Like C++ is probably more common than C#. C# is really popular in the Unity world, though. Yeah. Does Code Wars need a GitHub account? No, you can sign up using GitHub. And I think I have a link if you want to join, because we have a team for Clovis Community College. You can join the Clovis Community College team on Code Wars. It's not like you'll compete together or anything, but yeah. I'll post the link at some point. Okay, so let's get going on graph theory. So, shortest path. Let's say that each of these edges is the same distance. It's not, but let's just say it is. What is the fastest way to go from St. Paul to Springfield? Right there. Same distance, right? So St. Paul is 1 and Springfield is 5. If all these edges are the same distance, then it's actually the same route length to go 145, 125, 135, right? Because we don't have any distances on these things. Now, let me put some distances on it, and it's going to get a little more interesting, okay? So let's say that it is 100 miles from Minneapolis, St. Paul to Des Moines, which it's not, but it makes for a nice round number. And it's 100 miles from St. Paul to Madison, and it is 50 miles from St. Paul to Lansing, and it is 200 miles from Madison to Indianapolis, and it is 150 miles from Des Moines to Indianapolis, and it is 75 miles from Lansing to Springfield, and 50 miles, and 10 miles, and 50 miles from Indianapolis to Springfield. All right, what's the shortest route? If you wanted to navigate from Minneapolis, St. Paul to Springfield, maybe these things are minutes. A lot of times it makes more sense to think about travel in minutes rather than miles, because anybody who's driven through Los Angeles knows there's not always a one-to-one correspondence between miles and minutes, right? There sometimes a mile can take an hour, when it's rush hour in Los Angeles. Okay. So Arius has 135. What's the total distance there, Arius? What the heck? Why did I end up in AFK? How many languages do you need to know to get a job? 1? They're usually going to hire you for one language in particular, whatever the shop's language is of choice. And it's pretty common for a lot of scripting and things like that to be done in Unix shell script or Python or Perl and things like that. So it's fairly common for people to know other stuff like that. It kind of glues different parts of the business together. 1 to 5. Okay, so 1 to 2 to 5. Oh no, that was its length. Okay, so 125. So Arius has got a route of 125 miles, 1 to 3 to 5. Can anyone find a faster route? McCohen has 1 to 3 to 7 to 6 to 5, which is 110 miles. Yeah, so I think that is actually the shortest route. So this is the shortest route between Minneapolis, St. Paul, and Indianapolis. It doesn't seem like it should be, but they've got a bullet train and or an airport or something. I don't know. And so if you're talking about just total minutes traveled, it's faster to take this multi-hop route despite it being non-intuitive. Okay. So can you get a job just knowing C++? Absolutely. Absolutely. C++ programmers can be hard to find too. Like Paradox, one of my favorite game companies, they are constantly complaining about how hard it is to find people that know C++. So most colleges these days start you off on Python and then maybe Java, and then later on you kind of pick up C++. But you guys have been programming C++ since day one, so you'll probably, and also I teach you modern C++, which a lot of schools still don't. Some do, and more are teaching modern C++, but a lot of them seem stuck in the 90s. So. Berkeley does Python. The intro class at Berkeley is like in 2 different languages. It's in what's it called? They have some weird programming language they teach that is kind of pointless. C++ is very common. It's sort of this. It's kind of the reference language in that every language, since it either copies it or deliberately doesn't copy it. What is the class? Berkeley Introduction to Computer Science. Structure interpretation of computer programs. Yeah, 61. Scheme. That's right. Yeah. Okay. Yes, they use Python, and then they also teach Scheme, and they teach SQL. Okay, so fair enough. You guys kind of learned SQL secretly on the database project. I didn't teach it to you, though. I probably should. I probably should do a workshop on that at some point. SQL is really useful. It makes you very employable. I always thought C++ is easy until I heard it was difficult to learn. Yeah, it's got a reputation of being difficult to learn, but it really depends on who's teaching it. Okay, so this is a shortest paths problem. This is a classic graph theory problem. How do you find the shortest route from one place to another? Classic. Okay. So before we get into the actual algorithms for how to do this kind of stuff, let's talk about the 2 different ways that people hold graphs in memory. Okay, so the most basic and least commonly used way, but the most obvious way, is to hold it in a 2D array, right? So if 1 and 2 are friends, like let's say these are people on Facebook, if 1 and 2 are friends, and 2 and 3 are friends, then if you go to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, then if you go to row 1, column 2, you have a 1, and row 2, column 1, you have a 1, true, right? So if you have a true there, that means they're friends, right? Row 2, column 3, friends. That's that one. That makes sense? And then it's symmetrical. You see that? So if you draw a line down the middle there, you can see it's symmetrical. So you could actually probably throw away half the array. You could use something called a triangular array. In a case like this where you don't need half the array because it's symmetrical, you can implement something called a triangular array, and then you can save yourself half the RAM. Nice. I'll let you figure out how to do that. So, how much memory does this require? Now, normally when we talk about big O, we talk about time complexity, right? How long does it take to run? But here I'm going to be asking you about what's called space complexity as well. How much RAM does this take to hold? If I have N people on Facebook, how much RAM does it take to hold this adjacency matrix? First of all, do you understand the adjacency matrix? It's pretty straightforward, right? You just have a big 2D array of booleans, and if this is person 4, if you want to see if person 4 is friends with person 1, you go to row 4, column 1. Nope, they're not friends. Or you can go to row 1, column 4, same thing. They're not friends. Do you guys understand that conceptually? People, are you here? Did I explode your brains already? Yeah. Yes, very good, Mysterious. This is a order n squared. Order n squared. RAM requirement, right? So for Facebook, which has, I don't know how many billions of people, it would be quite a large number, right? Aaron, do you understand this? Like if I just handed you this, let me cover up the graph up here. And I asked you, is person 3 friends with person 5? Would you be able to look at this adjacency matrix and tell me? Aaron? Is person 3 friends with person 5? They're not? Or you can tell. So to tell if person 3 is friends with person 5, you go to row 3, column 5, and you check to see if that's true or false. If it's true, they're friends. If it's false, they're not friends. Okay. And since it's symmetrical, you could also go to row 5, column 3, and it's the exact same number. It's either way, it'll work. Okay. Like I said, there's something called a triangular array that you can use to throw away half the array to save on RAM a little bit. Can you explain why it is n squared? Well, this is a 5 by 5 array, right? So if you have 5 people, we have 25 elements in it. If we have 100 people, we would have 10,000 elements in it, right? So as the number of people gets bigger, the RAM requirement grows with the square, okay, of the number of people in Facebook or whatever. And the square of 3 billion is a lot of RAM. Okay. So for small graphs, this is actually quite doable. In fact, why don't we just hop onto the server and do it real fast. All right, so int n is equal to read how many people are in your social network. So we're going to make a two-dimensional vector of bools, true or false. Is this person friends with some other person? And it's going to be of size n, and each element of n is a vector of bools of size n. I don't know if you guys remember how to make a 2D array. That's how you make a 2D array using vectors, not arrays. Okay. So this is going to make a two-dimensional, it's going to make this. Right? The difference over here, by the way, this is Twitter. This is Twitter, this is Facebook. Facebook, it's symmetrical, right? 2 is friends with 3, 3 is friends with 2. So row 2, column 3, row 3, column 2, they're both true. for this one, person 5 is following person 1. Person 1 is following person 2, right? And so column 1, row 2 is true. Column person 2 is following person 3. So column 2, row 3 is true. So you can see this one's not symmetrical. This is Twitter. This is Facebook. So this is the problem that Zuck had? Yeah. It's one of the problems. There's a lot of scaling problems when it comes to having a graph that is billions in size. Like, you can't even, like, have all of it on one machine. So how do you partition it? You know? Like, how do you split it over multiple machines and traverse across the machines and things like that? Like, it's a hard problem, you know? And you're trying to advertise to them, so you're trying to make some sort of intelligent observations about these people so you can advertise to them too, right? So you need to not only traverse the network to find out who their friends are, but what their friends are interested in, and what their friends' friends are interested in, and all this kind of stuff. So this makes a 2D vector. The bools, kind of ugly, and I'm sorry it's ugly. There's nothing better, really. So, sort of. We could do this, I guess. Technically do that, except it's technically illegal, so we're not going to do that. Okay, so that's going to create a 2D array, and then we will just go into a while true loop and be like all int choice to read. Do you want to, 1, add a friend, 2, look up friends. So let's make a little Facebook right now. Okay? And these things are really easy to do when you got like 10 people. Right? It's still 100 booleans, but it's whatever, you know. It's not a big deal. So if or 3 quit, or whatever. If it's not any of those, it'll quit. So if choice is equal to 1, we'll add a friend. Else if choice is equal to 2, print all their friends. Else break. Okay. So oftentimes it's very useful to do the big picture part first before you get into the details on it. So, is this the only way to store it? No, it's not. There's better ways of storing it. This is, like I said, this is not the most common way of storing a social network. This is, it only really works for small graphs, but it'll show you how graph theory can work. So let's add a friend. Okay, so int friend 1 is equal to read. Enter the index of the first person. RIP 2. So we're going to type in an index. 0 and 5 are now friends, you know, whatever. And then all we're going to do is do a little bounce checking if friend 1 is less than 0 or friend 1 is greater than or equal to vec.size, or friend 2 is less than 0 or friend 2 is greater than or equal to vec.size, then break. A little bounce checking between friends, and then let's add it to the adjacency matrix. So vec.at technically, yeah, vec.at friend 1.at friend 2 is equal to true. So they're now friends. But what else do we need to do? This is Facebook. If you add somebody as a friend, they add you as a friend as well, right? What line am I missing? Oh no, we're not using pushback. Pushback will destroy the matrix. We're hard coding the size up front, which isn't very realistic, but we're making this an n by n matrix up front. If you do pushback, then yeah, I don't know, it won't be square anymore. Okay. Friend 2 needs to be friends with friend. Yeah, exactly. So we need to do this, and now we're good. Okay, and then to print all the friends of somebody, we just say for and I equals 0. I'll do size t. I equals 0. I is less than vector dot size I plus plus. And what we're going to do is get the index of the person who's friends. We're going to say which person do you want to print out their friends for? Oh, I can't call it friend, by the way. Whose friends do you want to look up? Okay. Person. So we're going to go through vector dot at person dot size, and of course we're going to bounce check this as well. If the person they type in is less than 0, or if the person they type in is greater than or equal to vector dot size, then break. Okay. So we're going to go through that row. Okay. So if they type in, we want to get all the friends for person 4, then it's just going to go through the row, and for each true that we find, we're going to say that person's their friend. So we're going to iterate across a row. So starting at the left side, going to the right side. If vector dot at person, because person picks out the row, then I is going to be which column dot at I is true. Then see out person I is their friend. And that's it. Okay. So there's going to be 10 people in my social network. I'm going to add a friend between person 1 and person 5. Add a friend between person 1 and person 9. Add a friend between person 2 and person 1. Look up friends for person 1. And there we go. So there's the friends. So this is a working social media website that will take over the world. Watch out, Zuckerberg, coming for you. Right. So that's it. This is a graph theory program. Okay. Any questions about this? So it's a 2D array. It's a 2D array, and basically when we add a friend, we just set the corresponding row and column to be true. And then if we ever need to look up, are they friends? We just go to that row and that column and look them up. What I'm doing is I'm printing all the friends somebody has. If I want to see who person 2 has as friends, I just start at the left and go to the right. So I go to row 2, and then start at column 0, column 1, column 2, column 3, column 4. That's what this is doing here. So I look up person 2, so it goes to vector.at2, that's row 2. And then it's going to loop from column 0 to column n-1. And if that value in the array is true, then it prints out that person's their friend. In every social media, would that be standard? No. Like I said, this array matrix thing is only useful for small numbers of people, because the RAM grows exponentially. Okay. Or not exponentially. Quadratically. Whatever. Yeah. What are friends? Yeah, you can't make a variable called friend, of course, because that's not allowed. Right? Can't have a friend. Sorry. No friends for you. You can call it friends. Yeah, you can't have a friend. You can have friends, but no friend. Okay. So, any questions about this? This is a simple implementation. Right? Friends are magic. That is right. That is right. That is what was her name? Twilight Sparkle? What was her name? Yeah, Twilight Sparkle. Okay, cool. All right. It's been a while. For My Little Pony. Yeah, that's correct. That's correct. She's the main character of the series. All right. Do you guys see the difference between the symmetrical and the non-symmetrical versions? You have an undirected graph on the left. You have a directed graph on the right. And there is a lot of terminology. There is a lot of vocab when it comes to graph theory, but all of it makes sense. All of it has real-life analogs, right? So I use Twitter as this analogy, but it doesn't have to be Twitter in every case, you know? Do you guys know what I mean by Twitter? Like, one person can follow a person. You can follow a person on Twitter, but they don't have to follow you back. Like, you have a one-way friendship, so to speak, right? When you add some movie star, when you follow some movie star, they're not following you back. Well, I mean, they don't have to, I guess. They could. So it's a unidirectional relationship. It's a directed graph. But these don't have to be, it doesn't have to be just social media. These could be streets, right? So this could be your average street where you can drive one way, you can drive the other way. These could be one-way streets, right? So if you're doing shortest paths, the shortest path between 1 to 5 isn't this way, because that's going the wrong way down the street, you know what I mean? So if you want to find the shortest path between 1 to 5, you got to take the one-way street here, the one-way street here, the one-way street here, right? And so graph theory is incredibly open-ended in terms of the problems it can solve, okay? These things could be pipes within your house, each vertex could be a room in your house, and the edges are where pipes run to, right? Like the analogies for this are pretty much limitless. Okay, so the other way of holding it is by doing... do I not have it in here? Okay, well, I'll just show you the other way of doing it, the better way of doing it. So this is called Adjacency Matrix implementation. So basically, for an adjacency matrix, just holds a big old array. Just is a big old array. Okay. So then there's another implementation called Adjacency List. And that is when we're going to do what Aaron said, which is to do pushback instead. So let's do that one. So I will show you the more common implementation now. And then we'll talk about your homework assignment. Somebody requested implementing Facebook, so we'll just do that. Okay. All right. So So rather than making a big square, right, that holds all the relationships, you make just you make all the vectors, but they're all empty. Okay, so it's going to be very similar, but it's going to eat up a lot less RAM in most situations. Okay. But you can make it without selling your private information to other companies. It's fine. It'll be fine. I'm sure you guys can implement Facebook. So do you see how very similar this is, right? I'm making a vector of vectors, but rather than kind of pre-allocating all of the relationships, I'm just going to leave them empty. And the reason for that is because I cannot have a relationship with 3 billion people, right? There's absolutely no reason for them to do a square relationship, right? Instead, there should just be a list of everybody that I'm friends with. And that list could be held in a linked list. I'm holding it in a vector here. Vectors can implement the list ADT. You just add things to the end of the list, push back. So when I create my account, I have no friends. And then as I add friends, it just appends to the end of the list. And then I'll have a list of people. So let's do this. Let's do it. So I'm just going to copy and paste a lot of this. You can see the difference in implementation. Add a friend or look up friends, add a friend. And again, I copy the skeleton of my code first. This is how I approach writing code. It's good to get all of your structure in place first. I found you can do it however you want, but this will compile, this will run, it won't do anything, but it will compile and run. You always want your code to be able to compile and run, right? Okay, so I think most of this actually I can copy. It's going to be very similar. Okay. This is the index of the first person, index of the second person if friend is less than 0. Okay. So rather than doing this, where it jumps to row 5, column 10, what I'm going to do is I'm going to go to row 5, and I will push back 10. 10. And so this is no longer going to be a vector of booleans. This is going to be a vector of integers. And so the integers are, so basically for every person, they're going to have a list of indices of the people that are their friend. So I'm friends with person 5, person 7, and person 2. Okay? So I could probably do this better with a set, huh? Because this would allow duplicates. Do you guys see what the problem is here? You see that? Like if I keep adding person 5 as my friend over and over again, it's just going to keep adding to the end. And I could do a search, but then the search is going to be expensive, right? Because it's not sorted in any way. So I would have to do an order in operation every time to stop duplicates. I should probably make this a set. Let's make this a set. Okay, so include set. And then rather than pushback, it will just be called insert and insert, just like that. Okay. So for each person gets their own binary search tree, and the binary search tree is the names of all the people that they're friends with. BSTs are good because we don't care about order. Yeah, we don't care what order you added friends, right? Do we? Nah, I don't think so. So this is pretty simple, right? So basically each person has their own binary search tree, and you say you're friends with 20 and 30 and 40, they just get added to the binary search tree, and then if you want to print who you're friends with, you just print out the whole binary search tree, right? So whose friends you want to look up? Copy and paste. Paste. Whose friends you want to look up? We do a little bounds checking, and then we can say for every integer in vector dot at person. So that's the binary tree in question. So for every each person has their own binary search tree, right? We made a vector of sets, and so we're going to grab the set corresponding to person 5 or whatever, and then we're going to say for every integer in that binary search tree, print it to the screen. Done. How many people are in my social network? 10. I want to add a friend. Person 1 is now friends with person 6. Person 1 is now friends with person 9. Person 1 is now friends with person 3. Add a friend. Person 7 is friends with person 1. And again, person 7 is friends with person 1. Look up friends for person 1. Here we go. Who are the friends of person 7? Person 1. Friends of person 9. Person 1. There you go. There's a working social network. Delete friends. You could. Yeah, that would be probably worth implementing. But this is something called an adjacency list. So basically, every time, I don't need to have 200 columns of booleans. 2 billion columns of booleans allocated for me. I can't be friends with 2 billion people or 3 billion people, right? Much better to just have a list of all my friends, and then if you ever need to iterate over my list, I can just do it this way, rather than iterating over 3 billion people. So adjacency matrices is just a 2D grid that holds true or false if you're friends, and an adjacency list, it's a little bit different. Instead, you just have a list of all the indices of your friends. Like I'm friends with person 2 and person 7, person 22, whatever. What's the big O for this one? Good question. So to look up if you have a friend on an adjacency matrix is what? Big O of space, big O of time. So for space, obviously, this is what happened here. For space, it's obviously faster. So adjacency matrices eat up more RAM, right? Because by default, if you don't have any friends at all, sucks to be you, you're kind of eating up no RAM, right? There's just a pointer to your empty tree. So sad. No friends, right? It's pretty much nothing. As you add more friends, the memory usage grows. And worst case scenario, if all 3 billion people on Facebook are friends with all 3 billion people on Facebook, the memory cost is actually worse, right? Because you've got not only, all 3 billion rows have all 3 billion columns, but rather than being booleans, which compress down nicely, they're integers, which are 32 times bigger, and you've got the overhead of all the sets and things like that as well. So if you're going to have everybody be friends with everybody or close to it, an adjacency matrix will actually eat up less RAM. But Facebook doesn't allow you to be friends with 3 billion people. Facebook limits you to 5,000. So it will... it is way, way less RAM to do an adjacency list instead. Okay. Now, for lookup time, if you want to look up if somebody is your friend, how much time does it take to look up if person 4 is friends with person 2? Who has 5,000 friends? Brandon Sanderson. Like I was saying, there's a lot of famous people that their friends list is full. To look it up in not for the list, not for the list implementation, for this implementation. What is the lookup time to find to grab a value out of an array? So if you've got a big array and you just want to grab row 4, column 2, or row 2, column 4, same thing, it's symmetrical. How long does it take to pull a value out of a matrix, out of an array? Order 1. Order 1. You just grab it. If you want to get it from constant running time. Yeah. Now, if you want to get it from this, what's the running time? If you want to see, is person 2 friends with person 27? What's the running time on that? It's order log n. Okay. the reason for that is because if you want to find out if person 1 is friends with person 27, it's an array lookup to grab, the row to grab that binary search tree. It's an order 1 operation. Then if you want to find out if person 27 is within that tree, that is a login search. Basically everything you do with a binary search tree is going to be a order login search. Okay. Could you speed it up with a hash table? Probably. Probably could. Depends if you want, how often you want to do this, right? Because binary search trees are actually better at doing this than hash tables. To dump the contents of a hash table is actually more expensive than it is to dump the contents of a binary search tree. Not significantly, but it is. So do you guys conceptually understand how to do this? Like, make a social network? Maybe. All right. Is there any code up here that is hard to understand? All right, so let's talk about your homework assignment. So, yeah, Arius requested it, so let's do this. So sudo deploy homework csci26 Facebook. Okay, there you go. There you go. So you are going to make an implementation of Facebook, and you're going to implement both Facebook and Twitter, essentially. So Facebook, if you add a friend, they add you. With Twitter, it's a unidirectional. You can follow Jennifer Lopez without her following you back. Okay. So what do you have to do? You have to be able to add new users. Users are all single names, like Bill, Bob, Cindy, J-Lo. You have to have users become friends or followers. If Bill adds Bob, then Bob adds Bill in Facebook mode. But in Twitter, Bill can add Bob without reciprocation. You need to print out all the friends of just one person. Sounds very similar to what we just did. They must be printed in alphabetical order. Well, thank goodness we're using sets. And then you'll need to print out the entire social network. So you need to traverse the graph, and we need to talk about how to do that. Okay. So you don't know how to do number 4 yet. Okay. And then you need to print out everybody ever in Facebook. So you should be able to do all of this right now except for number 4. Okay. What was the other homework assignment? I've got a lot of graph theory assignments. I've got a lot of them. So, this one's probably the easiest to do, maybe. I don't know. It's hard to say. I sometimes do a graph theory in 41 also. Did you guys do the Bacon number one in 41? Bridges. I did that, I think, 2 years ago, where you compute the Bacon number. So you grab data from the IMDb, sort of, and iterate outwards from Kevin Bacon. Grab all the movies Kevin Bacon's in, then you grab all the people that are in movies with him and tag them with a Bacon number of 1. And then for each of those people, you grab the movies they're in, and then you grab the actors in those movies and tag them with a 2 if they weren't already processed. You kind of go outwards. Actually, the same algorithm for this, actually. Okay. Yeah, mountain bridges. We that's another graph theory one we could do too. Okay, so let me show you how to traverse a graph. That's pretty important. So you can do number 4. So let's erase the annotations. Okay. Oh yeah, this is important. Trees are a kind of graph. So binary search trees and stuff. That's a graph. You see that? It's got vertices connected by edges. Hey, cool. The root is 7. The root of the tree is 7. Trees in computer science grow downwards for some reason. I don't know why, but they do. So This is a directed graph. It's not bidirectional. It's unidirectional. It's a directed graph. And it doesn't have any cycles in it. So this is something called a DAG. Okay. This is a term you will hear computer science people use a lot. I was watching a talk on Git the other day, and they said Git involves DAGs. And you're just kind of expected to know what that means. You like DAGs? You like DAGs? DAGs. You like DAGs? It's from Lock, Stock, and Two Smoking Barrels. So a DAG is a directed acyclic graph. Okay. Snatch! Damn it. You're right. You're right. Okay. Yeah, so it's directed, which means it's not bidirectional. No, sir. It is unidirectional. It points in one direction. Acyclic means that there is no, like, circle formed by the things. This would be cyclic. It's not cyclic, it is acyclic. And it's a graph. So if you look at how GitHub works, or Git specifically, you'll have, like, a version of your source code, and then it might branch, and then people might merge it together and stuff like that. But there's no cycles formed. There's no circular dependencies. Okay. So DAG is a term that you will hear computer science people just toss out like that, like DAGs. Okay. Yeah. So a binary tree has 0, 1, or 2 kids. Every node, every vertex has 2 children, or less in a binary tree. But there are trees that you can have more than 2 kids as well. So it's a binary search tree. It's a graph. So how do you search a binary search tree? Well, for a binary search tree, I'm sure you guys all know how to search a binary search tree, right? Like you've all taken 41, I think, mostly. No? Okay, well, let me show you. So if you have a pointer to the root here, and let's say you're going to see if 4 is in the DAG. What you do is you come in here and you're like, okay, I'm looking for 4. You come in here and you're like, all right, is that 4? No. Okay. Well, since this is a binary search tree, all numbers, the rule for a binary search tree is that, what's up? Food? Later. Thanks. Thank you. Because it's a binary search tree, the rule for a binary search tree is that numbers in the left subtree, this would be the left subtree over here, and this is the right subtree over here. All numbers found within the left subtree are smaller than 7. That's the rule. From whatever point you are in the tree, everybody to the left is smaller, and everybody to the right is bigger. Okay? Doesn't matter where you are. If we're here, everybody to the left is smaller, everybody to the right is bigger. Okay? If you're here, everybody to the left is smaller, everybody to the right is bigger. So, this can be used to accelerate searches, because you're coming in here, you're looking for 4, you're like, okay, this isn't 4, it must be to the left, because 4 is smaller than 7. So you come down here, we're at 3. Okay, well, it must be to the right. Okay, we're at 6, it must be to the left. Oh, found it. Now, if I was searching for, like, 18, it would go to the right, go to the right, go to the right, go to, oh, null, not found. So that's how binary search tree searching works. Dungeon Delve, yeah. Dungeon Delve was a binary search tree assignment. So, that's how you would, like, search a binary search tree. But if you want to traverse the tree, if you want to just print everything out, there's a couple different ways you can do it. You can do it in order, where you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which looks kind of weird. It would go like this. You can go through the tree like that, which looks kind of gnarly. Actually really easy to code, but looks gnarly. That's called depth first search. Depth first search is when you go deep first and kind of work your way through the tree that way. And the other way you can go through a tree is using something called BFS, breadth first search. And so for that one, you print out, like if you're going to print out this tree breadth first search, you'd print out 7, then 3, then 12, then 1, then 6, then 9, then 13, then 2, 0, 2, 4, 8, so on and so forth. So you go like this. So one way you can think about breadth first search is you print out everybody 0 away from the root, i.e. the root. Then you print out everybody 1 away from the root, 3 and 12. Then you print out everybody 2 away from the root, 1, 6, 9, 13. 3 away, 4 away, 5 away, and you sort of expansively move outwards through the graph. That's BFS. Okay. DFS is you go deep first, and then you work your way through the graph. BFS, you go wide. It's like concentric circles spreading outwards. Okay. So you will see these terms used all throughout computer science. BFS and DFS are just acronyms that like people use. How did you print all the friends of somebody on Facebook? I use BFS. Ah, that makes sense. Okay, so how do we do that? Okay, so to do a BFS on a graph, you print out wherever you start, and then you print out everybody that's connected to that one. That's 1 away. Then you print out everybody that's 2 away. Then you print out everybody that's 3 away, and so on and so forth. So if you have breadth first search, I think it starts, yeah, so the starting node is right here, and watch how it traverses the tree. So it starts off going 1 away, then it goes 2 away, then it goes 3 away, then it goes 4 away, then it goes 5 away, then it goes 6 away. Okay. Do you see how that works? It goes 1, 1, 1, 1, 1. And then after all the vertices that are 1 away have been touched, then all the vertices that are 2 away get touched, and then 3 away, and 4 away. That's would DFS have a faster runtime than BFS? Look at the 2 different animated GIFs. See which one's faster. They're each going to visit each node once. So they technically have the same runtime. Okay. The difference is how they traverse the tree. So with DFS, you can see it starts off. You can think of it as like go to the left every time or something. So it goes to the left, 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 and it just keeps doing that until it runs out of room, and then it tries going to the right, and then it goes to the left as far as it can until it runs out of room. Then it goes to the right. So this is like how you would solve a maze by like always make a left turn, you know, and then if you ever dead end, you back up and make the right turn instead. That's DFS. Whereas if you were solving a maze using BFS, you would start off wherever you are in the maze, and let's actually just download a maze. Yeah, sure. Okay. Can I draw this? No. Edit. Can I draw this? No. Can I draw this? Good. Okay. So let's say this is our starting location here. Okay. And we want to find a way out. Any way out. Doesn't matter. So each intersection could be considered a point on a graph. Right? None of this is interesting. Right? That's just an edge. And that's actually not interesting. It is not interesting either because there's no intersection there. Right? So there's actually a line that runs all the way this way. Do you see that? You guys understand what I'm getting at here? So none of this part of the corridor is interesting at all. Nothing's interesting until you get to a branch. So everywhere there's a branch, I'm going to drop a vertex. Right. Do you understand how I can convert this into a graph? Default photo app? Yeah, it is. So, that makes sense? How this maze can be transformed into a graph. Basically, everywhere there's a fork, then you make a vertex there. Okay. So let's solve this using DFS. So our rule will be go left every time, kind of marking down our path, and if we ever dead end, then make it the right instead. So if we're starting here, I guess we'll go left, and then we'll hook a left, and we go down this way. Oops, dead end, so we backtrack up, come up here, make a right instead, come up here. All right, make a left, we go over here, make a left, we go down here, make a left, no, sorry, this would be the left. Come over here, dead end, backtrack, 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 come up this way, over here, make a left, dead end, make a right, make a left, dead end, backtrack, over here, make a left, dead end, backtrack, make a left, been here before, backtrack. You have to remember where you've been before so you don't have, this is a loop, by the way. This is a cyclic graph, not acyclic. It's not a DAG, right? Because we just found there's a circle in this thing. Okay, so we came back to here, then we'll try this one. Go left, backtrack, come up here, backtrack, backtrack. Go over here, go left, backtrack, go straight, go left, backtrack, go right, and we are out. So we missed this exit over here, but such is life. Okay? So that is a depth first search. DFS. Okay. So always go left, and then backtrack once you dead end. Now we'll do it again with BFS. And we will use green this time, I guess. Okay. So starting from here, this is our starting vertex. We go one away and one away, like that. And then we go two away, nothing that way. Okay, up here. Two away, and then we try going over here. Two away, come over to here, and to here. So we're sort of moving out in concentric circles through the graph. And then we go three away here. Now, if we actually had to move physically back to each of these locations, BFS would be really bad, right? Because it'd be like, all right, mark this one. Okay, now backtrack all the way over to here and do this. No, okay. Then, all right, come over here and mark that one. Then backtrack. And it's really bad if you actually have to physically walk back each time, right? Because you're doing concentric circles. And then to here. And then we'll do four away, and we found the exit over here, and we found the exit over here. And then this one as well. Okay, so you kind of spread out through the maze. And so this is called BFS. Okay. And both will work. Both will find the maze. It's not like one is better than the other at solving a maze. If you have physical constraints, like where you have to physically walk, BFS is pretty bad, right? Because you have to walk here, and then, okay, now let's go check this person, go one over there. Okay, now let's go back over here and go one away. And then let's go back over here and go two away. And then let's go back over here and go two away. And then let's go back over here and go two away. Like if you actually had to walk it, BFS is quite bad. BFS does have an advantage, which is if the maze is infinite, then if it's an infinite maze, but with exits that are a finite distance away, DFS won't work. BFS will. Do you guys understand? Like if this maze kind of went on forever, like it's one of these video games that will just generate infinite mazes, right? If you just kept going left and going left and going left and going left and going left, you would quite possibly go infinitely that way and never find the exit. You guys get that? So BFS will work on an infinite maze. If you have an infinite maze with a finite exit, a finite distance away, BFS will find it, right? Because you go 1 away, 2 away, 3 away, 4 away. It will eventually hit it. DFS does not work on an infinite maze. Okay. So how do you code it? Well, there is a code pattern that I'm about to show you that is super, super useful. And this is my my way. It's not like I invented it, but it's my favorite way of traversing a graph. So we're going to build up a social network here, and then after we're done building it up, what are we going to do? We're going to print out everybody connected to one person, right? Because they don't have to be connected. Like persons 1 and 2 could be friends, and persons 3 and 4 could be friends, and they're a disconnected graph, right? They don't have to be, like, a graph doesn't have to all be fully connected, right? You can have a group of friends in Sacramento and a group of friends in Seattle that just none of the people in these cliques know each other or connected to each other, right? That happens. If you look at a road map of America, is it connected? Like the interstate system, right? Can you drive from, let's say, let's say the I-5. Let's say you're on the I-5, just considering interstate, it's not state highways or any of that stuff. Can you drive from the I-5 to any interstate in America? What do you think? Is it connected? If you start off on the I-5, over here near Corcoran or whatever, can you drive to any other interstate in America? It's an important question because different algorithms will work differently depending on if your graph is connected or not. Like I said, there's a lot of terminology in graph theory, and we sort of like categorize graphs different ways. For example, you can have a dense graph or a sparse graph. A dense graph has a lot of connections between it. A complete graph, everything's connected to everything else. A dense graph has a lot of connections. A sparse graph has a few connections. So which one do you think better represents Facebook or social networks? Do you think social networks like Facebook are complete, dense, or sparse? Out of all the people on Facebook, how many are you friends with? Let's put it that way. How many connections do you have coming out of your node on the social graph compared to the whole? Are you connected to everybody? Do you have a friendship with every person on Facebook? No. Do you have connections to most people? No. It is a very sparse graph. And there's different algorithms that are better at working on sparse graphs and are working on complete graphs, dense graphs, and then you have more terminology. You have a connected graph or a disconnected graph. Like this one. So is the interstate system connected or is it unconnected? Are there chunks of the interstate system that are traversable within their area, or can you go to any interstate from any interstate in America? Yeah, and that's one of the reasons why I think there's a 5K limit. It's because if their algorithms only work on sparse graphs, you don't want to have those few people that are connected to like literally everybody on the planet. So it'll probably explode their algorithms, right? The running time would go to hell. So is the interstate system connected or unconnected? The 5 isn't connected directly. Yeah, but it doesn't need to be, right? Like 1 isn't connected to 3. It just matters like, can you get to any interstate starting on the I-5? You know what I mean? What do you think? Is it a connected graph or is it an unconnected graph? And the answer is the interstate system is an unconnected graph. Anyone see the road on here that isn't connected? No? Let me turn up the resolution. So here is the interstate in Hawaii. Yeah. So Hawaii has an interstate because they wanted to get that sweet federal dollars, right? There you go. So there are interstates, in fact, in Hawaii because they wanted to get the federal money as well, and so they actually have some fairly nice roads that aren't technically interstate, in my opinion, because they don't go to another state, but it's funded with the federal interstate budget. So there you go. I was thinking about going to Hawaii this last summer, but the COVID situation was kind of, I might go for spring break. I don't know. We'll see. So I was in Hawaii. What year is it? 2015, 2016, something like that. Solid. Yeah, interesting. I just got back from a trip to Japan, and we were flying Hawaiian Airlines, which is a nice airlines, by the way. And so we had a layover in Hawaii. So I'm like, hey, we just spent a month in Japan. Let's go to Pearl Harbor. That was kind of fun. So. So, interstate highway on a state surrounded by oceans. Yeah, exactly. But you have to know that, right? Because like there are algorithms that will not work if you have a disconnected graph, right? If you have an unconnected graph, some algorithms just break. So you actually kind of have to know the attributes of your graph, and don't worry if all of this is like too much right now. The point is that even though these things look really simple, it's a vertex and an edge, and that's it. It's a dot and a line. There's all sorts of different attributes of graphs. Like some of them are connected, some of them are DAGs, some of them are trees. Like there's a lot of different kind of words we use to describe graphs. And the algorithm I'm about to show you is my favorite way of traversing a graph. So if I want to do a social network, friends of one person, or 3, print the social network of one person. So meaning if I'm friends with Sally and Sally friends with Sydney and Sydney's friends with Bob, it goes and prints out all of those people. Okay, so what you can do, we're actually kind of out of time, aren't we? What time does this class end on Tuesdays? 12:50. 17 minutes. Let's put this off for next time. I could probably do it in 19 minutes, but it'd be rushing it. So why don't you start on Facebook for now? You can probably get, with what we have here, you can probably get everything done except for the graph traversal. That's actually a pretty important topic. So we'll just do that on Thursday. Yeah, it's Tuesday. So any questions about graph theory? There's a lot to it. But I really like it. Like it's pretty. Yeah, it's like here's a traversal for depth first search. So if you want to print a tree in depth first search, you just print the left subtree, print me, print my value, print the right subtree. So if you have do I have trees on here? So the algorithm, even though it looks really complicated, like you're gonna come down here and then go up and then go down and then jump over there and da 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 da. It's actually a really simple algorithm. The algorithm is print everybody in the left subtree, then print my value, then print everybody in the right subtree. That's it, and it will create this very beautiful dance as it navigates through the tree. And if you have a binary search tree, it prints the binary search tree in order. It's 4 lines of code, right? Breadth first search is easy to do if your tree is held in array form. I don't know if you guys remember that from CSI 41, but you can actually store a tree as an array. And if you do that, you don't need to have pointers. So it actually cuts down on your memory costs. As long as your tree is kind of balanced, it doesn't waste too much memory either. And if it's full and complete like a heap is, then it really doesn't waste memory. And you can print out a tree breadth first search by simply printing out the array representation of it. So the root is held in array element 0, the left child of root is held in array element 1, the right child of root is held in array element 2, the left child of 1 is held in array element 3, the right child of 1 is held in array element 4. And so you literally just go down the array and just print out all the values, and there you've done a breadth first search of a tree. It's very easy. Okay. So if you're holding it in a pointer form, then the algorithm will be the one I'll show you on Thursday. Okay. Does the standard library have a DFS BFS function? Yeah. So like right here, where I'm saying for every element in that binary search tree, print out that element. That's doing a DFS. You don't see it. It's just automatic. But it starts off giving you the first element in the set, which is you start at the tree, you have to go all the way down to the bottom left, then it goes to the next one and the next one and the next one, and this is going to do a DFS traversal of the tree. And what that gives you is all the values in order. Sorted. Least to greatest. Okay. How many graph assignments we're doing? I'm planning on like 3. 3 programming assignments involving graphs, just because I like them a lot. Depends how well you all do. Yeah, well, here's sample graph. Look at that. Already giving you the graph traversal. Okay. Look at how generous I am. All right. Then let's see. Let's take a look at the README file. So the README file, friends are just strings, I think. Error handling, if you choose anything other than Facebook and Twitter, type anything else than 1 through 6. If you try adding somebody already in the system, that's an error. If you try to add a friend or follower that's already a friend or follower, that's an error. If you try to add somebody who's not in the system. Okay. So, all right, we'll just stop here for today. I think this is pretty good. you have any questions, get cracking on this, and we will pick it back up on Thursday. All right. Thanks, you guys. See you then.